A ground fault circuit interrupter, or GFCI, continuously monitors the current flowing through the hot and neutral wires. If it detects an imbalance between the two indicating a ground fault, it trips to protect against electrical shock. In this scenario, the hot wire from the circuit feeds the switch leg, which controls the light. The neutral wire is taken from the load side of the GFCI. This setup results in an unbalanced current flow. Current flows through the hot wire to the switch leg and the light. However, the current does not return through the neutral wire connected to the load side of the GFCI. Instead, it flows back through the grounded neutral of the electrical panel. This imbalance is detected by the GFCI's current transformer, or CT, which then trips the device. Consequently, the light turns off because it is no longer supplied with power. Connecting a switch leg to the hot wire and the neutral from the load side of a GFCI will trip the GFCI, interrupting power to the light. This is because the imbalance in current flow triggers the GFCI's ground fault protection mechanism. To understand this better, let's delve deeper into the principles of GFCI operation and ground faults. A GFCI is designed to protect people from electrical shock. It works by monitoring the current balance between the hot and neutral conductors in a circuit. Under normal conditions, the current flowing through the hot wire should be equal to the current returning through the neutral wire. The GFCI continuously measures this balance. If there is a difference of even a few milliamps, typically 4 milliamps to 6 milliamps, the GFCI will trip quickly, interrupting the power supply. This rapid interruption prevents a dangerous electrical shock from occurring. Now let's consider what happens when you connect a switch leg's hot wire to the circuit and the neutral wire from the load side of the GFCI to the light. The hot wire provides the path for current to flow to the switch and then to the light. When the switch is closed, current flows through the light bulb, causing it to illuminate. However, the neutral wire is not connected directly back to the source neutral. Instead, it is connected to the load side of the GFCI. This creates an unusual situation. The current flowing through the hot wire to the light does not return through the neutral wire connected to the GFCI. Instead, it finds an alternate path back to the source, typically through the grounding system of the electrical panel. This creates an imbalance in the current flowing through the GFCI. The GFCI detects this imbalance and interprets it as a ground fault. A ground fault occurs when current flows through an unintended path to ground. This can happen if a person comes into contact with a live wire or if there is a fault in the wiring of an appliance. Because the GFCI is designed to protect against ground faults, it immediately trips when it detects this imbalance. When the GFCI trips, it interrupts the flow of power to the entire circuit, including the light connected to the switch leg. This causes the light to turn off. The reason the GFCI trips in this scenario is that the current is not returning through the intended neutral path. The GFCI is designed to ensure that all current flowing through the hot wire returns through the neutral wire. Any deviation from this indicates a potential ground fault, which the GFCI is designed to prevent. To avoid this issue, always ensure that the neutral wire for a switch leg is connected to the source neutral, not to the load side of a GFCI. This ensures that the current flows correctly and that the GFCI functions as intended, protecting against ground faults and electrical shocks. Here are some additional points to consider. Firstly, it's important to understand the difference between the line side and the load side of a GFCI. The line side is where the power enters the GFCI, and the load side is where the power exits the GFCI to supply the downstream circuit. Secondly, GFCIs are designed to protect against ground faults, not overloads or short circuits. Overloads and short circuits are handled by circuit breakers or fuses. Thirdly, GFCIs should be tested regularly to ensure that they are functioning properly. Most GFCIs have a test button that you can press to simulate a ground fault and verify that the device trips. Fourthly, when wiring a GFCI, it's crucial to follow the manufacturer's instructions carefully. Incorrect wiring can prevent the GFCI from functioning properly or even create a safety hazard. Fifthly, if you're not comfortable working with electrical wiring, it's always best to consult a qualified electrician. Working with electricity can be dangerous, and it's important to take all necessary precautions to protect yourself from electrical shock. In summary, connecting a switch like hot to a GFCI load neutral will cause the GFCI to trip because it creates an imbalance in current flow. This imbalance is detected by the GFCI, which interprets it as a ground fault and interrupts the power supply to protect against electrical shock. Always ensure that the neutral wire for a switch leg is connected to the source neutral to avoid this issue. Understanding the principles of GFCI operation and ground faults is essential for ensuring electrical safety in your home or workplace. Remember to test your GFCIs regularly and consult a qualified electrician if you have any doubts about electrical wiring. Now let's talk about why it is important to understand the difference between a ground fault and a short circuit. A ground fault is an unintentional electrical path between a source of current and ground. This can occur if a wire comes loose and touches a grounded metal box, or if the insulation on a wire is damaged and exposes the conductor. A short circuit is an unintentional electrical path between two conductors of different voltage potential. This can occur if two bare wires touch each other. Ground faults are typically caused by insulation failure, loose connections, or accidental contact with grounded objects. Short circuits are typically caused by damaged wiring, improper connections, or conductive objects bridging conductors. Ground faults can cause electrical shock, fire, and damage to equipment. Short circuits can cause immediate and severe damage to equipment, fire, and electrical shock. Ground fault circuit interrupters, or GFCIs, are designed to protect against ground faults. Circuit breakers and fuses are designed to protect against short circuits and overloads. It's crucial to use the correct type of protection device for the type of fault that is likely to occur. GFCIs should be installed in areas where there is a high risk of ground faults, such as bathrooms, kitchens, and outdoor locations. Circuit breakers and fuses should be installed in all electrical circuits to protect against short circuits and overloads. Regular inspection and maintenance of electrical systems can help prevent both ground faults and short circuits. Look for signs of damaged wiring, loose connections, and insulation failure. If you suspect a ground fault or short circuit, immediately turn off the power to the affected circuit and consult a qualified electrician. Never attempt to repair electrical problems yourself unless you are properly trained and qualified. Electrical safety is paramount. Always take precautions to protect yourself and others from electrical hazards. Another factor to consider is that different types of lights, like LED versus incandescent, may have different effects on a GFCI circuit due to their varying current draw characteristics. An incandescent bulb will have a high inrush current when it is first turned on, but then settles to a steady state. An LED bulb has low current draw in general, but may have electronic components that could introduce harmonics or other noise on the line. In most cases, these differences are not significant enough to cause a GFCI to trip. However, if a GFCI is particularly sensitive or if there are other issues on the circuit, it is possible for certain types of lights to cause nuisance tripping. Also, consider the quality of the wiring and connections. Loose connections, corroded wires, or damaged insulation can create resistance in the circuit. This resistance can cause heat to build up, which can lead to insulation failure and potentially a ground fault. It is essential to ensure that all wiring and connections are in good condition and properly tightened. Furthermore, the age of the GFCI itself can be a factor. GFCIs have a limited lifespan and may become less sensitive or more prone to nuisance tripping over time. If a GFCI is several years old and is experiencing frequent tripping, it may be time to replace it. When replacing a GFCI, it is important to choose a high-quality device that is properly rated for the circuit. Always follow the manufacturer's instructions for installation and testing. In addition to GFCIs, arc fault circuit interrupters, or FSIs, are another type of protection device that can help prevent electrical fires. FSIs detect arc faults, which are dangerous electrical discharges that can occur when there is damage to the wiring or insulation. Arc faults can generate a lot of heat and can quickly ignite nearby combustible materials. FSIs are typically installed in bedrooms and other areas where people sleep, as these are the areas where fires are most likely to occur. While GFCIs protect against ground faults, SIs protect against arc faults. Both types of devices are important for ensuring electrical safety. It is also worth noting that the National Electrical Code, or NEC, provides detailed requirements for the installation and use of GFCIs and SIs. It is important to be familiar with the NEC requirements and to follow them carefully when working with electrical wiring. Some common NEC requirements related to GFCIs include: firstly, GFCI protection is required for receptacles in bathrooms, kitchens, garages, and outdoor locations. Secondly, GFCI protection is required for receptacles within 6 feet of a sink. Thirdly, GFCI protection is required for all 125 volts, 15 amps and 20 amps receptacles and dwelling units. Fourthly, GFCI protection is required for appliances such as dishwashers and washing machines. Fifthly, GFCI protection is required for electrical equipment used near pools, spas, and hot tubs. Remember, electrical work should always be performed by a qualified electrician who is familiar with the NEC requirements and local codes. Never attempt to perform electrical work yourself unless you are properly trained and qualified. Electricity can be dangerous, and it is important to take all necessary precautions to protect yourself from electrical shock and other hazards. To provide a more comprehensive understanding, let's examine the specific characteristics of a GFCI that contribute to its effectiveness in preventing electrical shocks. Firstly, the GFCI's ability to detect small current imbalances is paramount. As mentioned earlier, a GFCI is designed to trip when it detects a current difference between the hot and neutral wires as low as 4 mA to 6 mA. This level of sensitivity is critical because even small amounts of current can be dangerous to the human body. Secondly, the GFCI's rapid response time is crucial. When a ground fault is detected, the GFCI must interrupt the power supply quickly to prevent a dangerous electrical shock. GFCIs are designed to trip within a fraction of a second, typically 25 milliseconds to 40 milliseconds. This rapid response time significantly reduces the risk of serious injury or death. Thirdly, the GFCI's self-testing capability is an important feature. Most GFCIs have a test button that allows you to verify that the device is functioning properly. When the test button is pressed, the GFCI simulates a ground fault and should trip, interrupting the power supply. This self-testing capability ensures that the GFCI is always ready to protect against ground faults. Fourthly, the GFCI's immunity to nuisance tripping is a desirable characteristic. While GFCIs are designed to trip when a ground fault is detected, they should not trip unnecessarily due to normal circuit conditions. High-quality GFCIs are designed to minimize nuisance tripping while still providing reliable protection against ground faults. Fifthly, the GFCI's durability and reliability are essential. GFCIs are designed to withstand the rigors of daily use and to provide reliable protection for many years. It is important to choose a high-quality GFCI from a reputable manufacturer to ensure that it will perform as expected. When selecting a GFCI, it is important to consider the specific application and to choose a device that is properly rated for the circuit. GFCIs are available in different amperages and voltage ratings, so it is important to choose a device that is compatible with the electrical system. It is also important to consider the environmental conditions in which the GFCI will be used. GFCIs are available in different types, such as weather-resistant and tamper-resistant, to suit different environments. Weather-resistant GFCIs are designed for outdoor use and are protected against rain, snow, and other weather conditions. Tamper-resistant GFCIs are designed to prevent children from inserting objects into the receptacles, which can help to prevent electrical shock. In addition to GFCIs and SIs, surge protective devices, or SPDs, are another type of protection device that can help protect electrical equipment from damage. SPD protect against voltage surges, which are sudden increases in voltage that can damage sensitive electronic equipment. Voltage surges can be caused by lightning strikes, power outages, and other electrical disturbances. SPD are typically installed at the service entrance of a building to protect the entire electrical system. They can also be installed at individual circuits or appliances to provide more localized protection. SPD work by diverting excess voltage away from the protected equipment and safely to ground. This helps to prevent damage to electronic components and other sensitive equipment. When selecting an SPD, it is important to consider the voltage and current ratings of the electrical system, as well as the level of protection that is required. SPD are available in different classes and with different surge current ratings, so it is important to choose a device that is appropriate for the application. It is also important to have SPD installed by a qualified electrician to ensure that they are properly grounded and connected to the electrical system. Regular maintenance and inspection of electrical systems are essential for ensuring safety and preventing electrical hazards. This includes checking for damaged wiring, loose connections, and other signs of wear and tear. It is also important to test GFCIs enough size regularly to ensure that they are functioning properly. If you notice any problems with your electrical system, it is important to have them repaired by a qualified electrician as soon as possible. Delaying repairs can increase the risk of electrical shock, fire, and other hazards. Remember, electrical safety is a shared responsibility. By following these guidelines and taking appropriate precautions, you can help to protect yourself, your family, and your community from electrical hazards. Now let us get to some further examples of ground fault scenarios and how GFCI protection plays a critical role in preventing electrical shock. Imagine a scenario where a homeowner is using a power drill outdoors to work on a project. Unbeknownst to the homeowner, the power cord of the drill has a small nick in the insulation, exposing the bare wire underneath. As the homeowner continues to use the drill, the exposed wire comes into contact with a wet surface such as damp grass or a puddle of water. This creates a ground fault, as the current now has a path to flow to ground through the water and the earth. If the drill is not protected by GFCI, the homeowner could receive a severe electrical shock if they come into contact with the drill or the wet surface. The current would flow through their body to ground, potentially causing serious injury or even death. However, if the drill is plugged into a GFCI protected outlet, the GFCI would quickly detect the ground fault and trip, interrupting the power supply and preventing the homeowner from receiving an electrical shock. The GFCI would sense the imbalance in current flowing through the hot and neutral wires and would trip within milliseconds, cutting off the power before the homeowner could be harmed. Another example is a situation where a person is using a hairdryer in the bathroom. If the hairdryer accidentally falls into the sink filled with water, it could create a ground fault. The water would provide a conductive path for the current to flow to ground. If the bathroom outlet is not GFCI protected, the person could receive a severe electrical shock if they come into contact with the water or the hairdryer. However, if the bathroom outlet is GFCI protected, the GFCI would quickly detect the ground fault and trip, interrupting the power supply and preventing the person from receiving an electrical shock. These examples illustrate the importance of GFCI protection in areas where there is a high risk of ground faults such as bathrooms, kitchens, and outdoor locations. GFCIs are a critical safety device that can help prevent electrical shock and save lives. It is important to ensure that all outlets in these areas are GFCI protected and that the GFCIs are tested regularly to ensure that they are functioning properly. Additionally, it is essential to follow all electrical safety guidelines and to take precautions to avoid creating ground faults. This includes inspecting power cords for damage, avoiding the use of electrical appliances near water, and never touching electrical equipment with wet hands. By being aware of the risks of ground faults and taking appropriate precautions, you can help to protect yourself and others from electrical hazards.